Okay, the monetary approach to exchange rate. The first assumption, we have two main assumptions: the uncovered interest parity condition, the purchasing power parity condition. The uncovered interest parity can be expressed as the interest rate equal to foreign interest rate plus the percentage change in the exchange rate. Okay? The purchasing power parity in log, which in absolute value is internal price equal to exchange rate which multiply foreign prices, can be also expressed in terms of logarithm as small pt, so the log of price, equal to st plus small p star, using the log. Okay? Now, so uncovered interest parity and purchasing power parity. We have these two assumptions. Then we have to consider the equilibrium in the money market, because this is the monetary approach to the exchange rate. So we assume that the income or GDP or consumption is exogenous. It's given by nature. Okay. So the equilibrium in the goods market using the log of each variable can be expressed as the nominal money, the log of the nominal money stock, small m, minus the level of price. This is the real money stock in log. Okay, is the log of nominal money stock divided by the level of price, which is the log. Okay, the real money stock is MT divided by PT. Okay, if we apply the log to this, we get log of nominal money stock minus the log of prices, applying the property, and this is equal to MT, which is the log of nominal money stock, minus PT, small pt, which is the log of prices. So the real money stock is this, and we have the inequilibrium in the money market. The real money stock should be equal to the money demand, real money demand. And we assume that real money demand is linear. Okay? Is a linear function. It is equal to alpha 1, which is a parameter, which multiply the level of exogenous consumption, which is given in this model, minus a parameter alpha 2, which multiplies the interest rate IT. So applying, let me repeat again for people at home, okay? The real money stock should be equal to the real money demand if we apply the purchasing power parity and the uncovered interest parity. We get this equation, and from here we have the dynamic equation of the exchange rate in the monetary approach to the exchange rate. What we have to do is to have an equation, a relation between S dot T and ST. This is a differential equation in ST, in the exchange rate. And it's easy to get S dot T from this equation. as 1 divided by alpha 2, which multiply the exchange rate, minus 1 divided by alpha 2, which multiplies nominal money stock minus foreign prices plus alpha 2 foreign interest rate minus alpha 1 the level of exogenous consumption. So this equation gives us the dynamics of the exchange rate. This part of the differential equation, this is a differential equation in the exchange rate, okay? This part contains or includes all the exogenous variables. This part is exogenous. Nominal money stock, foreign prices, foreign interest rate, and the level of consumption is exogenous in this model. So we can call this part, omega t, and our differential equation that we need to solve becomes s dot t equal to 1 over alpha 2 st minus 1 over alpha 2 omega t. And we need to solve this differential equation. Solving this differential equation, we understand the dynamics of the exchange rate. So our differential equation is the derivative, the percentage change in exchange rate equal to 1 over alpha 2, the level s of t, minus 1 over alpha 2, which multiplies the exogenous force in this model. Now, the phase diagram can be used also in this case, because in this case, we have an equilibrium solution for the exchange rate, yes. It's enough to impose that s dot t is equal to 0, which implies percentage change equal to 0. So the equilibrium solution, we assume that is positive, and it's positive because the exchange rate is positive. Anyway, it's log, so maybe also it's negative. But if this is the equilibrium solution, and we put here s dot t respect to st, due to the fact that alpha 2 is a parameter greater than 0, okay, the phase diagram is an increasing function. So we can see that the equilibrium solution we can call S bar is globally unstable, as we have seen yesterday. But yesterday the money demand was an implicit function. Now we have an explicit money demand function which is linear. So we have dynamic instability because if the exchange rate is here, the exchange rate depreciates. Small s, okay? Because now we are considering the log, small s, okay? If the exchange rate is here, you have a continuous appreciation in the exchange rate. So this is globally unstable. This solution is globally unstable. Anyway, we will solve backwards the differential equation just to solve the model, but we know that we will need to solve it forward looking, because if we solve backward looking, we will get a solution which is globally unstable. So a solution in which if we have a difference between the initial value and the equilibrium value, you will go toward plus infinite or toward minus infinite. We know from the phase diagram. Okay? It's clear? And yesterday we have seen also the economic explanation of this dynamics, showing that if the exchange rate is greater, you have a reduction in real money stock, so an increase in interest rate, and so a further depreciation. Okay? But now I want to show you how to solve backward this model, and for the forward solution, which is really difficult, I will give the final solution. Okay? So it's an intermediate level. Okay? Okay. Now, how we can solve this differential equation? I write again the differential equation. The differential equation is s dot t, so the derivative of this with respect to time, equal to 1 over alpha 2, which multiplies st, minus 1 over alpha 2, which multiply the exogenous components, the exogenous variables. Now, to solve this, we know that we need to write this as s dot t minus 1 over alpha 2, which multiply st, equal to minus 1 over alpha 2, which multiplies omega t. Okay? This is the differential equation. We need to multiply both sides by the integrating factors. The integrating factors is, we know this. What is the integrating factors in this case? To multiply by the integrating factor, so it's e to the power of minus t over alpha 2. This is the integrating factor, okay? T divided by alpha 2. Yes, is the integrating factor. Now the problem is that we need to integrate these two sides of the differential equation by between 0 and t. So we need to change the variable. Okay? What I'm saying now, we need to integrate both sides of this equation, but because we need to integrate between 0 and t, because this is a backward looking solution, is a solution between 0 and t, from the initial time until now, from 0 until now. And this part becomes the derivative of S, we call now time v, because t is the extreme of integration. So we need to use another variable, but it represents time, okay? So SV, which multiplies e to the power of minus v over alpha 2, this derivative with respect to v, we are applying the same rule we have seen for the differential equation. In dv, because this is an integral. Okay, the derivative, just to check the condition, the derivative of this function is, the derivative of the first is s dot v, which multiplies the second function, e to the power of minus b over alpha 2, plus the first function s v, which multiplies the derivative of the second function. But the derivative of the second function is the same function, e to the power minus v over alpha 2, which multiplies the derivative of the exponent, so which multiplies minus 1 over alpha 2. This is equal to, collecting e to the power of minus v over alpha 2, we get s dot v, okay, minus 1 over alpha 2 SV, which multiplies e to the power of minus v over alpha 2. So this is equal to this derivative. Now it's clear. This is quite clear. You can check to see the video at home. The second part is the integral between 0 and t of minus 1 over alpha 2, which multiplies omega v, because now time is v, e to the power of minus v over alpha 2 in dv. This is the other integral. So now, how we can compute the first integral? It's quite easy, because differential and integral are inverse functions. dv and dv simplify, okay? And we get, in the first part, SV, the exchange rate, which multiplies e to the power of minus v over alpha 2 between 0 and t. We need to compute this function between 0 and t, because this is the backward solution between 0 and t. And the second part is minus 1 over alpha 2, which is constant, so we can put outside the integral between 0 and t of omega v e to the power of minus v over alpha 2 in dv. The first side of this part is the value of this function on t, and the value of minus the value of the function on 0. So we have, I need to delete, we have st e to the power of minus t over alpha 2, which is the value of the function if v is equal to t, okay, minus s0 e to the power of 0 if v is equal to 0. And the right hand side is minus 1 over alpha 2 integral between 0 and t omega v e to the power of minus v over alpha 2, correct? Yes. In dv. Okay, perfect. So the solution of this exchange rate, try to understand this point. The solution will be st e to the power of minus t over alpha 2. This is 1, okay? E to the power of 0 is 1. So it's equal to S0 minus 1 over alpha 2 integral between 0 and t omega v e to the power of minus v over alpha 2 in dv. Okay? So we can get st as st equal to s0 minus 1 over alpha 2 integral between 0 and t omega v e to the power of minus v over alpha 2 in dv, which multiplies e to the power of t over alpha 2.
Okay, now what we have to do is to obtain a relation between interest rate and real GDP in order to have a relation similar to the curve, which is the IS relation. And we get, we will put all the factor with the interest rate on the left hand side and the rest on the right hand side. So we have on the left hand side M2 plus B2, which multiplies the interest rate, which is this term and also this, equal to, we put first the exogenous variables. So we have C0 plus I0 plus X0 plus the government expenditure fixed at 11 G bar minus the propensity to consume, which multiplies it out some tax. And then we have the other part which we collect y. You can easily check that if the computation is exact, but in this case we will have minus 1 minus C1, which multiplies with 1 minus t is the denominator of the multiplier, minus b1 plus m1, which multiply the level of income. You can easily check that this you can obtain this relation from the previous. We can call this alpha. Okay, we can call with alpha. So alpha is the sensitivity of the total expenditure to the interest rate, which is given by the sum of the sensitivity of imports and investments. This is the autonomous part of aggregate of the total expenditure, we will call it A, and this coefficient, which is the denominator multiplied, we will call it B. So finally, we can write the IS relation as alpha I equal A minus BY, which implies that I is equal to A divided by alpha minus B divided by alpha, which multiplies income, and is the IS relation. We can also prove this relation is this slope is negative, and this is the intercept. So the IS relation in the space interest rate income is this. So this is the IS relation. So the intercept over alpha and the slope is negative. This negative relation displays the set of interest rate y and real GDP, which is the goods market. If we start from point A, for instance, and we in this point we have equilibrium in the goods market. If the interest rate goes down, we have no equilibrium in the goods market, implying that given this level of income, at this point we can call it B. We will have that the total expenditure will be lower than income. Why? Because of the it's the opposite. It's greater than income. Greater than income because of the lower interest rate, and this will imply through the multiplier effect an increase in income toward the point C, equilibrium point C. The same may apply to an increasing interest rate, which leads to a reduction in total expenditure. If you imagine an increasing interest rate in point D, the total expenditure is lower than income because of the higher interest rate, which decreases the level of investment and net exports, and this should lead to a reduction in GDP through multiplier effect because of the lower total expenditure. So this is the IS relation. Given the intercept of the IS relation, which is A over alpha, is the IS relation, if we have an increase in A, then this an increase in A the shift, the curve, the relation will shift on the right. Why? Because we have an increase in the autonomous demand, in the exogenous demand. Or we can have an increase in A, because, for instance, we have an expansion in the fiscal policy, which increases government expenditure, reduces the lump sum taxes, or a positive demand shock like increasing household trust, firm trust, say zero, I zero, or GDP, exit zero. All these factors will shift the IS relation to the left. The opposite holds. If you have a reduction in A, typical examples are the recessionary or restrictive fiscal policy, reducing government expenditure, increasing lump sum taxes, or negative demand shock like reduces in firms or households trust and or GDP are examples that shift the IS relation on the left. Another thing that we have considered in the LM relation, remember LM is increasing in this space. The expansionary monetary policies implies a shift on the right of the relation of the LM relation, while restrictive monetary policy, it's better to call them A and B. So expansionary monetary policy shift the LM to the right, restrictive monetary policy shift the LM to the left. And this is what we now we have to derive